Hello everyone, welcome back. In this video we're going to explain one of the other metallic crystal structure, hexagonal closed pack. If you remember, as a review, we said that we have two terms, crystal system and crystal structure. We said the crystal systems will be cubic, hexagonal, triclinic, orthorhombic. There are others, crystal system we call them, crystal system. And we said that those are the way that the lattice shape or the unit cell shape will be. Beside those, we said that we have crystal structure. Now, crystal system is the shape of the, I would say, the lattice or the unit cell. And we said crystal structures is relating the way that atoms arrange themselves within this crystal system. Now, so far, the one that we explained them, all of them, they were cubic. We'll come back to some of the information. We said simple cubic. So the system was cubic and the arrangement was simple. We said face-centered cubic. Again, a cubic system. Face-centered, we say we have atom at each face. And we explained body-centered cubic. Again, still it's cubic. And we said body-centered, there is an atom at the center of the body, but still the system is cubic. Now this system we have it here, it's hexagonal. Hexagonal closed pack. Now the shape is no longer cubic, it's hexagonal. It's one of the common crystal structure we have it. You see that magnesium, zinc, titanium, some others, they have this crystal structure. Now, here we're going to learn the same thing that we learned on cubic. The atom arrangement, number of atoms in a crystal structure, coordination number, relation between the lattice parameters and radius of atom. Now here we have two lattice parameters, A and C. We have two lattice parameters, A and C. The way that they called hexagonal is basically because of the 6 atoms we have it here at each corner, that they will create a hexagonal shape. So if I continue, I can draw another hexagonal here. Goes like this. This is hexagonal. I can create, for example, another hexagonal from, let's say, from here. I can create it. Goes like this. Come here. We can create hexagonals and we will have this crystal structure. And the way that comes down, this will be, and again the hexagonal will create it back here. Now why the arrangement is important? Why? Because we will understand how many atoms we have it inside this crystal structure, and later we will understand the way that those atoms are arranged. We call them direction plane. We will understand many more things later. Now the arrangement, what will be? We have hexagonal at the top, hexagonal at the bottom. At each hexagonal corner, so hexagonal we have 6 corners. At each corner there is one atom. This is the reduced sphere. We said this is not the exact way. This is how the atoms touching each other, but this is for understanding. So we have 6 atoms at each corner of the hexagonal, 6 atoms again at each corner of the hexagonal. We have it there. So if I just go for numbering them, 1, 2, 3, 4, 5, 6 corner here and 6 at the bottom, that's going to be 12. Then we have 1, you can see it in the surface, we call it, at the surface of the hexagonal here. and one at the bottom of the bottom face of the hexagonal, and 3 will be in the middle. 3 will be in the middle. Here, I don't know if you can see them. One will be at this, they will try to manage them between the gap here. Those 3 gaps are going to be 3 atoms there as well. Well, remember, we're not going to say total 17 atoms inside one crystal structure. Why? Because not all of them are exactly inside the hexagonal. Remember, from the cubic, we said that the corners will be shared between 8 cells. Now here, the corner atoms, look at this corner atom here, the corner atom here. There is 3 here, there's 3 here, and 3 above, yes? Because if I continue, I can draw this crystal structure, for example. There will be hexagonal at the top as well, because those are, so the continuous. So if I take any of the corner atom, let's say we're taking this corner atom here, change the color. Let's say we're taking this corner atom here. Well, 3 will be down, look, 3 will be down, and 3 will be top, so each corner atom here, each corner atom will be shared between 6 unit cells. This is why, because it's hexagonal. It's hexagonal. Each corner atom will be divided by 6, because it will be shared between 6 unit cells. 6 unit cells. Those are the corners. Why? Because look at here on the plane 3. So if you think of with the 3 dimension, 3 will be the bottom, 3 will be the top. So each atom will be shared between 6 unit cells. That's why each corner will be 1/6. Each corner will be 1/6. How many corners we said we have it? We had 12, because 6 at the top, 6 or so. The top will go for 12 corners. 12 corner. Each corner will be 1/6. 1/6. So it's going to be 2 atoms came from there. 2 atoms came from the corners. Now, number 13, which is the face, and number 14, again the face, face are still the same. This will be shared only between 2. The face atom, for example, if I check this face atom here, this face atom, it's going to be shared with the bottom and with the top. So it's going to be shared between 2 unit cell. How many phase do we have it? We have 1, 2 phase. So you have 2 phase atom. Each of them will be shared between 2 cells, 2 unit cell. So it will be 1/2 for each of the unit cell. And that's going to be 1 atom there. Now, however, the one in the middle are completely inside the unit cell. So there will be 3 interior and completely inside it, and that's going to be 3 there. So total number of atoms here will be 6 atoms. Now if you remember, I told you in the cubic maximum number of atoms would be 4. Now here we have 6 atoms, but why? Because the volume is bigger. Still, this is we call closed pack. Closed pack means that the atom cannot be more packed than this. They cannot be more packed than this. Even this is 6 atoms, but because of the volume, still the packing, we're gonna talk about the packing factor in the next video, still will be the same. Still will be the same. We're not gonna be the highest packing. It's for the closed pack. Closed pack, the name of closed pack means that the atom will not be compacted more than that. They have minimum void between them. The arrangement of the atoms will provide minimum void. This is how the arrangement of atom here means 6 atoms at the corners, 6 at the bottom as well. 1 in the top phase, 1 in the down phase, 3 in the middle. It's gonna give us a hexagonal closed pack. Hexagonal closed pack. So we have 6 atoms, 6 atom total. Let's just calculate it here as well. the way that we calculate it. Now, we need something else. Now we said that when we want to calculate the relation between the A and the R stands for the atom radius, A stands for the lattice parameter. If you want to calculate the relation between them, we need what? We need a sliced one. I mean slicing. Why? Because we don't need, this is 1/6 of the atom is here. It's 1/6 of the atom. So from this, we understand those are touching each other. Look, those are two touching each other. So if this is, I mean, this is supposed to be in the center of it. I mean, if you start to from center to center, this is the hexagonal. It's the hexagonal. So if this is from the center to center, that's going to be 2r. 2r. And we know that this is, we called what? The side, we call it A. A in hexagonal closed packing crystal structure is equal to 2r. However, C cannot be related to the just the radius. Why? Because, yeah, the way that they have it, the gap between them, or the size of the atom, it's deciding this C. However, there is a typical value that we're using it. I mean, ideal ratio they call it, ideal ratio, that most of the element may have this, the ratio between C and A, the ratio between C and A. But this is not always the same. If nothing is given to you, we will use this ideal ratio. C divided by A will be 1.633. Sometimes some of the crystal structure, hexagonal crystal structure, C over A is changing because of the atom size. They might change, but ideal ratio, I mean C over A, will be 1.633. So this C will be bigger than A. So since we know A, we can also relate, because we know A is equal to 2R, and we know C is equal to what? 1.633. I couldn't write it. So this is equal to 2R. And we know that C over A is equal to 1.633. So I know that C is equal to 1.33, A and A is equal to 2R. So I can simply write 2 times C will be 2 times. If it is the ideal ratio, we can write 2 times 1.633R. This is the ideal, the ratio between C and R, A and R, that we can use it to calculate the volume of this hexagonal. Now the volume of hexagonal is not a cube. Now it's the area of this base, There you have it. You can find the area of this base times C. It's going to give you the volume. So the area of this base times C is going to give you the volume. Now I'll provide you the volume of hexagonal, V equal to something. I'm going to provide it to you as an equation so we can use it whenever we need to calculate the volume of hexagonal unit cell. A hexagonal unit cell, we can calculate it easily. Now, one more thing that we're supposed to, I'll just explain it here. It is the coordination number, the way that the atoms are going to bind, the bonding. Bonding basically means when they touch each other, we have bonding. So the bonding may be physical, maybe chemical. We're not going to go into deep. But here as well, one atom, it's touching 12 other atoms. Well, take this one. There will be 6. So there will be 6 atoms. There will be 6 atoms that touching. There's 6 here. And there will be 3 at the bottom. 3 at the bottom. And there will be 3 more at the top. 3 more at the top. So if I take this one, let's say that if I'm taking this to, let's see if you can understand this guy here. There is one here. I mean this guy here, will touch 12. 6 will be at the top of it, 6 will be at the bottom. So 6, 6 will be 12 coordination number. I mean coordination number, it means that the maximum bond that this and the atom can have it, I mean touching 12 other atoms. So it might be physical bonding, chemical bonding, but the maximum coordination number here is this crystal structure will be 12. I mean here it can be easier to understand. 1, 2, 3, 4, 5, 6, rounding it, 3 at the bottom, and since there will be 3 at the top, that 3 as well touching this one, that's going to be total 12 atoms touching each other. That's going to be coordination number. The coordination number same as FCC. We said that look, FCC also it's the, and as we said that FCC is also it's the highest packing that atoms can do in FCC, similar to hexagonal crystal structure. That's why the maximum number of coordination that they have it will be 12. The same thing as in FCC. Now we'll come back to atomic packing factor in all of them. We'll explain it in one video for closed packed. So I'll come back to this one. Alright, let's explain this before. Okay, let's take this one into. I'll leave it to explain the atomic packing factor, then we'll come back to this one. So after atomic packing factor, I will explain this, the difference between FCC, HCP. I mean, if someone interested to see how the material will be in FCC or PCC, FCC or HCP. Thanks for watching.